Institute of Engineering and Technology. Today we are going to discuss few more topics of sequence and series. So let's begin with the first topic, that is nth term test for divergence. If a positive term series un is convergent, then limit n tends to infinite un is equal to 0. The converse of above theorem is not true. That is, if limit n tends to infinite un is equal to 0, then series un need not be convergent. So what this theorem says, that if a positive term series is convergent, then this limit n tends to infinite un will always be 0. But we cannot write in the converse form, that is, if limit n tends to infinite un is equal to 0, we cannot always say that the series un is convergent. Okay, so this gives a test for divergence. That is, if limit n tends to infinite un is not equal to 0, then the series un is divergent. So we will use this test to prove some example. That is, we will show that this limit n tends to infinite un is not equal to 0, and then we can say that this series un is divergent. Okay, so let's begin with the example. Show that the series n square upon 5n square plus 4 diverges. So here un is given, that is n square upon 5n square plus 4. Now we will apply limit. So limit n tends to infinite un equals to limit n tends to infinite n square upon 5n square plus 4. Okay, take n square common from denominator, it will get cancelled. So what remains is limit n tends to infinite 1 upon 5 plus 4 upon n square. Okay, and we know this limit n tends to infinite 1 upon n is equal to 0. So this term is 0. So what remains is 1 upon 5, which is not equal to 0, right? Therefore, we can say that the series is divergent by nth term divergence test. Okay. Next, is the series 1 plus 4 plus 7 plus 10 plus 1 is convergent? So we will check whether the series is convergent or not, right? So now here all the numbers are given. So firstly we will find un. Okay, so the formula to find un is this, that is Tn is equal to a plus n minus 1 into d. Okay, this a means first term. So from here your first term is 1 plus n minus 1. D means difference. So 4 minus 1 will give you 3. Okay, just simplify this. So you will get 1 plus 3n minus 3. On further simplification, 3n minus 2. So this is your un, that is nth term. Now we will apply limit. So limit n tends to infinite un is equal to limit n tends to infinite 3n minus 2. So when you apply infinite, so you will get this answer infinite, which is not equal to 0, right? So we can say that the series is divergent by nth term divergence test. Okay, next, Cauchy's integral test. Let f be a continuous, positive and a decreasing function on the interval 1 to infinite, and un is equals to f of n. Okay, this is given. Then the series un converges or diverges if the improper integral 1 to infinite f of x dx is finite or infinite. In other words, we can write as if integration 1 to infinite f of x dx is finite, then series un is convergent. And if integration 1 to infinite f of x dx is infinite, then the series un is divergent. Okay, so here we have a f, which is a continuous positive decreasing function in the interval 1 to infinite, right? And here the un, nth term, is some function of n. Okay, so now to check whether the series is convergent or not, what we will do is we will find this integration 1 to infinite f of x dx. Okay, and if this integration is finite, then the series is convergent. If this integration is infinite, then the series is divergent. Okay, so let's begin with the example. Check whether the series 1 upon n square plus 1 converges or diverges. So here un is given, that is 1 upon n square plus 1. This is a function of n, right? This is given. Now we will write in the form of x. So in place of n, we have to just write x. Okay, so you will get 1 upon x square plus 1. Now this function fx is continuous, positive and decreasing function on the interval 1 to infinite. So we will apply this integral test, right? Means we have to find this integration 1 to infinite f of x dx, that is integration 1 to infinite f of x is what? 1 upon x square plus 1. Okay, now this integration is improper, right? So in place of here infinite, we will substitute b and will apply limit. So we have limit b tends to infinite, integration 1 to b 1 upon x square plus 1 dx. Okay, now we know the integration 1 upon x square plus 1 dx is what? Tan inverse x, right? So just apply this integration, so you will get limit b tends to infinite tan inverse x and this limit 1 to b. Now just apply the limit, so you will get tan inverse b minus tan inverse 1 and this limit b tends to infinite. Okay, now apply this limit, so you will get tan inverse infinite minus tan inverse 1. Now we know tan inverse infinite is pi by 2 and tan inverse 1 is pi by 4. Simplify this two, so you will get answer pi by 4, which is a finite term. Okay, so by Cauchy's integral test, what we can say, that the series is convergent, right? Now one more example. Test the convergence of a series n from 2 to infinite 1 upon n log n. Okay, now here the series starts from n is equal to 2. Why? Because for n is equals to 1, if you will substitute n is equal to 1 here, so you will get 1 upon log 1. And we know the answer of log 1 is 0. So it will become an undefined term. So we will start the series from n is equal to 2. Okay, now here un is given, that is 1 upon n log n. This is your function of n, f of n. So firstly we will write in the form of f of x. So it is 1 upon x log x. Okay, now this function fx is continuous, positive and decreasing function in the interval 2 to infinite, right? So we will find this integration 2 to infinite f of x dx. Okay, now the answer of f of x, that is 1 upon x log x dx. Okay, again we have improper integral, so we will write here m and limit. Okay, so limit m tends to infinite, integration 2 to m, and we will rearrange this term as 1 upon x upon log x. Okay, and we will apply this formula, that is integration f dash x upon fx dx is equal to log fx. Okay, so your function is given and its derivative, that is 1 upon x, it is present in the numerator, right? So we will apply this formula and answer will be log of log x and the limit is 2 to m. Okay, now we have to apply this upper limit and lower limit. So you will get limit m tends to infinite log m minus log 2. And as you apply this limit m tends to infinite, you will get this limit will tends to infinite. Okay, so we can say that by Cauchy's integral test that the given series is divergent. Now one more example. Test the convergence of series n from 1 to infinite to tan inverse n upon 1 plus n square. Here un is given, that is 2 tan inverse n upon 1 plus n square. This is f of n. Okay, so firstly we will write f of x, that is 2 tan inverse x upon 1 plus x square, which is a continuous, positive and decreasing function in the interval 1 to infinite. So we will find this integration 1 to infinite f of x dx. Okay, that is integration 1 to infinite f of x is 2 tan inverse x upon 1 plus x square. Okay, now again we have an improper integral, so we will write in this form, that is limit m tends to infinite, integration 1 to m to tan inverse x upon 1 plus x square dx. Okay, now we will suppose this tan inverse x as t. Okay, so Now take derivative, so you will get derivative of tan inverse x is 1 upon 1 plus x square into dx is equal to dt. Okay, now we are changing the variable, so we will change the limit also, right? So now this is the limit for x, so means when x is equal to 1, so t will become tan inverse 1. Okay, and we know the answer of tan inverse 1, that is pi by 4. And when x is m, okay, so you will get t as tan inverse m. So now we will substitute everything in this integration. So you will get integration 1 to infinite f of x dx is equal to limit m tends to infinite integration pi by 4 to tan inverse m to t dt. Just integrate this, so you will get t square by 2, 2 will get cancelled, and just apply the limit. So you will get limit m tends to infinite tan inverse m whole square minus pi square by 16. Okay, now apply this limit, so you will get tan inverse infinite whole square minus pi square by 16. Okay, now we know the answer of tan inverse infinite, that is pi by 2. So square it, so you will get pi square by 4 minus pi square by 16. Simplify this, so you will get 3 pi square by 16. Okay, so which is again a finite answer. So by Cauchy's integral test, the given series is convergent. Next, the limit n tends to infinite 1 upon n is equal to 0, but series 1 upon n is divergent. We have to prove this. Okay, so let's begin with the solution. Here un is given, that is 1 upon n, which is function f of n, right? Now firstly we will write in the form of f of x, that is 1 upon x, which is a continuous positive and a decreasing function on the interval 1 to infinite, right? So we will find this integration 1 to infinite f of x dx. Okay, now this function is 1 upon x, so integration 1 to infinite 1 upon x dx. Okay, now again we have an improper integral, so we have to apply limit. So limit m tends to infinite integration 1 to m 1 upon x dx. Now we know this integration, that is ln x. Okay, and the limit is 1 to m. Apply the limit, so you will get limit m tends to infinite ln m minus ln 1, which tends to infinite as m tends to infinite, right? So the answer of this integration is infinite. So by Cauchy's integral test, what you can say that the series is divergent. Okay, so now we have proved that the converse of nth term divergence test is not true. That is, this limit is 0. We can clearly see that if you will apply limit n tends to infinite 1 upon n, it will be equal to 0, and this series is divergent. So the converse of nth term divergence test is not true, right? So what we have studied in today's session, firstly we studied this nth term test for divergence. So what we have here, that is limit n tends to infinite un is not equal to 0, then we can say that this series un is divergent. Okay, next we study this Cauchy's integral test. Okay, so what we have here, this un is f of n, right? And this f of n should be a continuous decreasing and positive function. Okay, so we will find this integration 1 to infinite f of x dx. Okay, so if your answer is finite, then the series is convergent, and if answer is infinite, then the series is divergent. Okay, so I hope you have understood in this session. Thank you for watching.